Welcome back. We're going to have a short video here on roots that come in pairs. Okay, so we've seen plenty of real roots. We know we have linear roots like x minus 1 and x plus 2. We know we have quadratic roots like x minus 2 squared, cubic, x minus 4 cubed, so on and so forth. Okay, but we've also discussed briefly roots that come in pairs. So we're going to look at a random quadratic equation here, 2x squared plus 3x minus 4. Now, hopefully that's not factorable. I just made it up, so I'm pretty sure it's not. So in order to solve what the roots are here, the solutions for when p of x is equal to 0, we need to use the quadratic formula. So x equals the opposite of b plus or minus the square root of b squared minus 4a and c all over 2 times a. So I get negative 3 plus or minus the square root of 9 minus 32, that's negative 23, all over 4. And hopefully we all remember that a negative inside a square root means we have to bring an I outside. Well, this is the only way you're going to get an imaginary number, is if you have to use the quadratic formula or you have a negative inside your square root. And every time you have a negative inside your square root, you're going to have that plus or minus there. Okay? So if you have a plus or minus, this is two roots. It came in a pair. This is what's called a complex number because it has a real and an imaginary part. Complex numbers. So if that complex number is a root, we have to say complex roots come in pairs. Okay, and that whole plus or minus is the reason why. Another example, say you factored it down to x minus 3 and 2x squared plus 1. Right, it was a cubic that factored. Well, here, x equals 3. No problem. This one, though, says x squared equals negative 1/2. Your next step is to take the square root. And whenever you take a square root, you got to write plus or minus. Okay, so again, it came in a pair because it has a plus version and a minus version. Okay, so not only do complex roots come in pairs, but they come in conjugate pairs. So in fact, they come in conjugate pairs. All right, a conjugate pair means you have one plus and one minus, 3 plus I and 3 minus I. Okay, the same is true for irrational roots. They also come in conjugate pairs. Okay, we saw in the previous video where we were talking about the rational root theorem, we saw we had like, what was it, negative 3 plus or minus a square root of, I don't remember, 13 over 6. Okay, so that was a irrational number, which also comes in pairs. All right, so those are two things you want to take out of this. And we've seen this before, but we will touch on it again, the sums and products. If 3 plus I is a root, that implies 3 minus I is a root. So the question is, what quadratic do they come from? Well, the annoying way to do it would be x minus the root and x minus the root. And we could distribute that all out. So we have x minus 3 minus I, x minus 3 plus I, and now distribute, we get x squared. Getting monotonous already, minus 3x plus ix. That's only distributing the x. Now I get distributing the negative 3, I get negative 3x, I get plus 9, I get minus 3i. Now I got to send this guy through. Minus ix plus 3i minus I squared. Combine like terms, x squared, done, minus 6x, ix and negative ix cancel out. Negative 3i and 3i cancel out. And negative I squared is positive 1, so that's a plus 10. Excuse me. Okay, or we can use sums and products. If I add 3 plus I to 3 minus I, 3 plus I plus 3 minus I get 6. If I take the product, 3 minus I times 3 plus I get 9 minus 3I plus 3I minus I squared. Well, those guys cross out. Minus an I squared is plus 1. I get 10. Notice we have here 10 and 6. X squared minus the sums of x plus the product. Okay, so your linear term comes from the sum of your roots. Your constant term comes from the product of your roots. Okay, so the bottom line here, things that come in pairs, irrational roots and imaginary roots or complex roots. And the best way to find what equation they came from if you have the roots is to use your sums and products. Again, we'll do some examples of these later. So long.